Hello everyone, Mehdi Murtazavi here with another topic in engineering thermodynamics. So today I'm going to talk about the Maxwell relations, and that is in chapter 12 of this textbook that we are using in this series of courses. So first of all, the Maxwell relations are used in order to correlate the pressure, volume, temperature, and entropy of a simple compressible system. So let me just write this down. The equations that relate the partial derivatives of properties P, pressure, V, specific volume, T, temperature, and S, entropy of a simple compressible system to each other are called the Maxwell relations. Okay, so the Maxwell relations are based on the Gibbs equation. So we have four Gibbs equations, and the Maxwell relations are based on those four equations. So the very first relation or equation we have in a Gibbs equation is du is equal to TdS minus PdV. Okay, so this is one of the four Gibbs equations that we utilize for Maxwell relations. Now, in case you are wondering where this equation came from, so in fact it comes from applying the conservation of energy on a differential system. Let's say in that system we have Q going into the system, but that Q is internally reversible, minus work leaving the system, which is again internally reversible, and that is equal to du. So all I'm trying to do here is to obtain this equation. So on the right side, I'll do a couple of steps to come up with this. Now, I know that in internally reversible condition, that the, delta Q is equal to TdS. So delta Q in an internally reversible condition is equal to TdS. Likewise, this work can be written as PdV. Delta W for an internally reversible condition is PdV. Okay, so if I combine all these equations here, I can say, all right, TdS minus PdV is equal to du. Okay, so basically du is equal to TdS minus PdV. This is exactly what I have here. The other Gibbs equation that we are using here is dH is equal to TdS plus VdP. So this is one of the Gibbs equation. This one is one of the Gibbs equation. This is another Gibbs equation. And in case you're wondering where this is coming from, basically this comes from the continuation of this part. Okay, so if I continue here by saying that all right, so what I'm going to do, I am going to utilize the fact that H is equal to U plus PV. Okay, H is enthalpy, U is internal energy, and etc. So basically, based on that, dH is equal to du plus PdV plus VdP. PdV plus VdP. Okay, now what I'm going to do, I'm going to rewrite this equation based on that. Basically, instead of du, I will write the left hand side of this equation. So basically, I continue here, dh, instead of this du, I put the right hand side here. You know what? In fact, this u should have been lowercase because this is a specific volume and this is a specific entropy. So the unit is kilojoule per kilogram. So these two are pretty much the same thing. So dH instead of du, I would say TdS minus PdV, all right? And then I have plus PdV plus VdP. So this negative PDV will be cancelled with this one. So this cancels that, and I will end up with dH equal to TdS plus VdP, which is right here. Okay, so this is the one of the Gibbs equation that we are using today. This is another Gibbs equation that we have. Okay, so these are the two Gibbs equations that we have. The third Gibbs equation that we are using for Maxwell relation comes from the Helmholtz function. So the Helmholtz function says A is equal to U minus TS. Okay, so that's the function. So based on that, dA is equal to du minus TdS minus S dt. Okay, so let me give numbers to these equations. So let's say this is equation number 1, this is equation number 2, this is number 3, and for number 4, I'm going to use the Gibbs function. Gibbs function is G equal to H minus TS. So that's the function that we have. So once again, I can say dG is equal to dH minus TdS minus SDT. So dG is equal to dH minus TdS minus SDT. All right, so for the next step, what I'm going to do, I'm going to combine equation 1 and 3. And before that, let me also give number 4 to this equation. So I'm going to combine these two equations together. Okay, by saying combining, I mean instead of du that I have in equation 3, I'm going to write the right hand side of equation 1. So basically 1 and 3 give me dA is equal to, instead of du, I would say TdS minus PDV, right? And then getting back to equation 3, so basically this part, this TdS minus VdP is this du, which is coming from equation 1. The right hand side of equation 1 is this one here. So if I get back into this equation, I have minus TdS and I have minus SDT. Okay. So obviously this TdS cancels this one, and I will have dA equal to negative PDV minus SDT. So let me call this one equation number 5. For the next step, I'm going to combine equations 2 and 4. So previously I combined these two, but now I'm going to combine 2 and 4. So 2 and 4 give me, I will start with dG, let's say the left hand side of equation 4. So dG is equal to dH, but instead of dH, I will write TdS plus VdP. All right, so this is replacing my dH, but this is coming from equation 2, obviously, similar to what we did before. All right, so getting back to 4 minus TdS minus SDT. So this TdS cancels this TdS. And I will end up with dG equal to VdP minus SDT. So let me call this one equation number 6. If I notice my equations 1, 2, 5, and 6 are in the form of this equation that I had before. So maybe let me write it as a bullet item. So equations 1, 2, and also 5 and 6 are in the form of dz equal to m dx plus n dy that we had before. So previously, in our previous discussion, we had this form of equation, right? And I can apply the same form, or I can see the same form, let's say, into equation number 1. Okay, for example, if I do that in equation number 1, my z value is going to be u, or the internal energy. My m value in this equation is going to be temperature in equation 1. Oh, you don't see equation 1. Sorry about that. So once again, if I do that, I will realize that my z value in equation 1 is going to be my u, internal energy. My m value here is going to be my temperature. My x value here, or x parameter here, is my entropy, and so on. And I will see the same trend not only in just equation 1, but also in equation 2, 5, and 6. Okay? So that means I can form 4 cases by defining like these parameters in these 4 equations. For example, let me go to the next page. In case 1, I'm going to make my 4 cases. So in case 1, I'm going to apply that equation into equation number 5. So in equation number 5, this is what I had. If I get back to equation 5, this is what I have in equation number 5. And in that equation, z is a, m, capital M, is negative p, x is v, specific volume, n is negative s, and y is T, temperature. So let me just write this down. So in this case, in case number 1, M is negative P, N is negative S, Y is temperature T, and X is a specific volume. Okay, so that is one case. Now, the other case that I can form, let's say case 2, by the way, so in case 1, I applied that to equation 5. Equation 5. In case 2, I'm going to apply that to equation 6. Okay, so if I apply this general form of equation here, if I apply this general form of equation to equation 6, then my M is going to be V, my X is going to be P, my N is going to be negative S, and my Y is going to be T. So let's do that. M is going to be V, N, negative S, Y is T, and X is P. Okay, now the other case that I can make, case number 3, is obtained by applying that equation on equation number 1. So let's say if I do that in equation number 1, then I will get M equal to T, N equal to negative P, Y equal to V, and X equal to S. And finally, my case 4 will be obtained if I apply that general equation into equation number 2. So in that case, M is going to be T, N is going to be V, Y is going to be P, and S is going to be entropy. Okay, now that I have these 4 cases, I'm going back to this main equation that I had. So this was the main equation that I had. If you remember, next to this equation, in our previous discussion, we had an equation like this. We proved that partial m over partial y, once x is constant, is equal to partial n over partial x once y is constant. So what I'm going to do in the next step is to apply those m, n, x, and y into this form of equation. So I'm going to put my parameters into this equation. Okay, again, I will have 4 different cases, right? But this is my model. So let's do that. All right. Okay, so if I do that, my case 1, so let's apply this equation into my case 1. In that case, partial m is going to be negative partial p over partial y is partial t, okay? And that is when x is constant and x here is when volume is constant, is equal to partial n over partial x, which is negative partial s over partial v when y is constant and y being the temperature. Okay, so this is coming from applying this equation, this form of equation, into case number 1. And in case you're asking where this equation came from, you should see the previous video, because in the previous video we proved this general form of equation which is applicable whenever we have 2 independent variables. Okay, so let's do this equation to case number 2. If I do that, then my partial m is going to be partial v over partial y, which is partial t, when x is constant and x being pressure is equal to partial n partial x, which is negative partial s partial p when y is constant and y being the temperature. Okay, so let's apply this equation into case 3. So partial n partial y is partial t partial v when x is constant, x being the entropy, is equal to partial n partial x, which is negative partial p partial x is partial s when y is constant and y being the volume. And finally, I can do this general form of equation into case number 4, and that gives me partial m partial y, which is partial t partial p when x is constant and x being s entropy is equal to partial n partial x, which is partial v partial s when y is constant and y is pressure here. Okay, so these are the 4 equations that I have, and we call them the Maxwell relations. So each of them can be used separately, which is extremely useful. So these are my Maxwell relations. So these Maxwell relations are extremely valuable. The reason that they are valuable is because they can provide a method to determine the change of entropy simply by measuring the temperature, pressure, and the volume. All right? So let me just write this down. The Maxwell relations provide a method to determine the change in entropy by simply measuring changes in pressure, volume, and temperature. So if you remember, previously we mentioned that we have 2 types of properties. One type of property is a property that is pretty simple to measure, including pressure, temperature, and volume. So basically, this type is very simple to measure. The second type of properties are not really easy to measure, including entropy. So what we are doing here in Maxwell relations, based on these correlations, we can determine the change in the entropy based on properties that are easy to measure.